The second speaker for today is Yanpeng from University of Geneva, who will talk about Gelfand Zeitlin via Ginzburg Weinstein.
Thanks for the introduction, and thanks for the invitation for this wonderful event. The talk today is based on John's work with Anton and Jeremy like 2 years ago, and some part is an ongoing project with Xiaomeng. So in the title you see 4 names. So I will try to explain the first 2 and the second part. So let's begin. Let's see what's Gelfand Zeitlin system. So suppose we have the set of n by n Hermitian matrices, we denote it by Hn, and I joined at the bottom. And then since it's Hermitian, we can take its eigenvalues. Hermitian means the eigenvalues must be real. Since they're real, we can order them. So we order them such that lambda 1n is the biggest and lambda nn will be the smallest. So next, we will take the bottom right submatrix of A, as I draw here. And it's a k by k Hermitian matrices. We can take its eigenvalues as well. And let me denote it by lambda ik. They are real, we can order them, and we draw all the eigenvalues together like here. So more than all the inequality, like the order of the eigenvalues, there are more inequalities between these eigenvalues. They're the so-called interlacing inequality. What does it mean? It means the second line, this one, has to be in between of the first 2. And this guy must be in between of these 2. And it looks like this and like this. So, and now with all these eigenvalues, actually what I did is I defined a map from the space of Hermitian matrices to Rn and to Rm. So here m is 1/2 times n plus 1. That's the total number of all the eigenvalues. So this, I denote this map by f, and the image of the f will be a cone, like a real cone in Rm, and I denote this cone by C, like cone Gelfand Zeitlin. So what's the relation of this with Poisson geometry? So if we consider the compact group K equals to Un, the group of unitary n by n matrices, we know on the dual of its Lie algebra, it has a linear Poisson structure, which is a KKS bracket. Now with the let me denote a subset of H, Hn0, all the matrices with all like all the eigenvalues such that the inequalities must be strict. And actually one can identify the space Hn and Un. So it means on Hn we have a Poisson structure. And more than that, the maximal torus of UK acts on this space as well. So how does the action looks like? We take an element in the maximal torus, which is diagonal matrices, and we first use this T. We first pick some element U in UK such that it diagonalizes AK. So AK is part of A, so the other part we don't care, but we diagonalize the AK. And this is how we give, if we have this U and the T action is defined in this adjoint action. Because we are taking elements in this Hn0, all the eigenvalues are different. So this action is well defined. More than that, actually, for all the different TKs, their action, they commute. So altogether, we have a torus of this size. Why don't we have the Tn action? Because Tn action is trivial. Once we diagonalize it, you times T right and left, you just get the trivial action. So that's the total torus action here. So then, in the paper of Greenman and Sternberg, they showed the top line, like the eigenvalue, the eigenfunctions here actually is a complete set of Casimir functions of the linear Poisson structure. And what about the other functions? So for each k, this set of functions, the moment map for the tk action. So more than that, actually on this dense subset Hn0, it admits a global action angle coordinates. So and the Gelfand Zeitlin cone will be the image of the moment map for all the torus action, and this will be the torus we saw before. Okay, so this is very nice, but unfortunately, this method Glimmen-Steinberg invent only works for k equals to un or sun and sonr. If you use the classification of semi-simple Lie algebra, it's just type A and type BD. So, and recently there's a paper by Benjamin and Jeremy. They use a method of toric degeneration to construct global action angle coordinates for any compact Lie group rather than abelian group. So this is just a paper appeared maybe recently. So the talk today is trying to suggest another approach using Poisson Lic groups and cluster algebras to construct global action angle coordinates for compact Lie group. But at this moment, it only works for SON and SU. So actually, the old work with Antoine Jeremy is for SU, and the ongoing project I'm doing with Xiaomeng, we're trying to use some other method to generalize it to SO, and hopefully we can do it for SP. So now let's explain what's Poisson Lic group and what's the cluster algebra, or like the cluster algebra we use here. So Poisson Lic group is a Lic group together with a Poisson structure pi, such that the multiplication map on the Lic group is a Poisson map. So one side you have a Poisson manifold, the other side the Poisson structure is the one from it's a so-called product Poisson structure. And here we have some examples. The first one is what we know is the linear Poisson space, and the group structure here is just abelian, but the Poisson structure here is non-trivial. And also we have this one can be generalized to any compact Lie group, and on the dual of the Lie algebra we have this linear Poisson structure. And another one, I will not write down the detail. So on this compact Lie group we have a standard Poisson structure. It comes from the standard R matrix. So about Poisson Lic groups, all the Poisson Lic groups come in pair. So as we saw in the linear case, so the linear structure here, or the linear Poisson structure here actually comes from the, can you hear me?
Yes, it's breaking up a little bit, but not too bad. Now we can actually hear you.
In the linear case, we know this Poisson structure actually comes from the Lie bracket from UN. So there's some duality between Poisson structure and the Lie structure. That's why all the Poisson Lic groups comes in pair. So on one side you have the Lie bracket and Poisson structure, and then you can take the dual. It will give you another Lie algebra structure and Poisson structure. And so I will not explain the detail, but there's one example. So on one side we have the Lie group K, and with a 0 Poisson structure. And this is a Poisson Lic group, obvious. And actually its dual is just K star with a linear Poisson structure. So following so then let me denote k star pi k star, the dual of this.
Yanpeng, I think we lost your sound. Yanpeng? Yanpeng, if you can still hear us, perhaps it's worth disconnecting and connecting again. That's very unfortunate. Okay, yeah. Hopefully he heard us. Let's see. There's Yanpeng.
Yeah, it seems
Hi.
Hi. So let me share the screen again.
Yep. Okay. Good.
So where are we?
Yeah, we can see it very well. Yeah.
Okay.
Perfect.
So I don't know where I stopped.
We lost you for maybe 20, 30 seconds.
Okay. Then let me just maybe repeat. So here, K star as group is just upper triangular matrices with real diagonals. That's K star. So, and since we have a Lie group and we can since it's a group, we have the identity point, and by the property we need the multiplication to be Poisson map. One can show that actually the Poisson bivector at the identity is just a 0. Because of this, one can get a Poisson structure on the tangent space, which is just G. And by Cohn's linearization theorem, so capital K star and little k star with their corresponding Poisson structure are locally isomorphic as Poisson manifold. And later, by Ginzburg and Weinstein, they showed they are not only locally isomorphic, but actually globally isomorphic. But of course, here they are isomorphic as Poisson manifold, not Poisson Lic groups, because on one side we have an abelian group, and on the other side we have sorry, I see. Yes, the little k is Lie algebra of capital K, and the K star is a dual. They are isomorphic. Sorry. And on one side it's the abelian group, and on the other hand, it's not abelian. So they cannot be isomorphic as Poisson Lic groups. So the other thing is that the original proof is more like an existence proof. And moreover, one can say this isomorphic is not unique. Why? Because on one side, you can always precompose some other Poisson isomorphism, so it still gives you a global Poisson diffeomorphism between little k star and capital K star. So this map is highly non-unique. And later, there are several proofs about this map. So there's one by Boch using Stokes phenomenon, and one by Eilinghoff using the formal solutions of some PDE, and also one by Anton using using Moser flow. And actually, in the case of k equals to UN, Anton and Marinkin, they construct a explicit Ginzburg-Weinstein map. Have a linear Poisson structure, we'll do some strange scaling. We consider the scaled Poisson structure by S, and we still have a Poisson diffeomorphism between these two spaces. Okay, now we have this map. Let me give you one example. So for K equals to SU2, so which is Hermitian matrices, little k star we identified with Hermitian matrices. And under this Ginzburg-Weinstein map, it becomes upper triangular matrices with diagonal rail. And this last entry is given by this function. So because I put S here, so that's why there's S in all these coefficient. And the R is just a square root of rho square plus x square. Yeah, this map looks like some exponential, but actually it's not. And actually this is the only map I know which I can write down. So, and that's one of the difficulty of this project. We have some formula or some map, but one cannot really write it down. So like what I said, in the K equals to UN, we will just use the one constructed by Anton and Marican as our choice. So their map is good because it satisfies some conditions, and if it satisfies that conditions, it has to be unique. That's what we want to use. Next, let me explain what's the cluster chart we use for K equals to UN. So let's consider the matrix, the upper triangular matrices, and we take this submatrix and write dirt ik as its minor. So here, this is the matrix from the n minus k plus 1 row to n minus k plus I row, and the size is I times I, and because we always take it attached to the last line, so you know where to start. So then let me tell you, and for all the k, I and k satisfy this condition, we take them. That's all. This will be some functions on upper triangular matrices. So let me illustrate it in another way. So dirt 1n will be just this corner by definition, and 2n will be these ones, and you can continue. So for k equals to n minus 1, so actually we take the minor here, and we can continue. So for the smaller one, we always lower one row and then take the anti-diagonal matrices and take its determinant. That's in of this dirt ik. Okay, with all this preparation, I'm ready to state one of the main theorem of this talk. If we take an element in the Hermitian matrices, which is isomorphic to UN star, and apply the Ginzburg-Weinstein map with scaling S. So now this become a matrix in the upper triangular matrices. Then we take its ik minor, and then take the absolute value, take the logarithm, and take it over, divided by s, and set s goes to infinity. And it turned out this will be just the eigenvalue, the sum of some eigenvalues of A. And this sum is determined by this index I and k. So in some sense, if we define this as our functions on A, like on Hermitian matrices, this will give us a maximal commuting functions. And actually in this paper, we have some result for the angles, but due to the time, and I will only focus on the action coordinate here. Okay, now this is about type A, like for SON or UN, SLN or UN. So we want to do it not just for type A, but for the other type. And to do this, I need to put, I need to have some other input, which is called Poisson involution. Suppose we have a Poisson map, a Poisson manifold. A Poisson involution is nothing but a Poisson differomorphism such that tau square equals to 1. Once we have a Poisson involution, we can get another Poisson manifold. So suppose let x tau be the open set of the fixed locus of x under tau. Suppose one can write the bivector on x as AI wedge bi. Sorry, there's a typo. And then let me define another vector, which is AI plus wedge BI plus. Here A plus is just 1/2 of A and plus a push forward of A through this involution tau. And this pi tau will give you a Poisson tensor on X tau. So, okay, why we care about the Poisson involution? Because once we identify UN and UN star, SON actually is a fixed locus of UN under some involution. And this involution is simply given by A goes to A bar on UN. Because here UN, as we know, UN is the one, I mean, here when we identify UN and UN star and HN star, this involution will become A goes to minus A bar on the Hermitian matrices. And on the K star set, we have an involution which maps X to its inverse conjugation. And Xiaomeng has the following observation. Both tau and iota and eta are Poisson involutions for this Poisson manifold.
Yanpeng?
Was pointed out in both cases, but there the Ginzburg-Weinstein is the one from Stokes phenomenon. And here it's just this observation is for the AI map.
Yanpeng,
And
I think we lost you for maybe 10 seconds. Maybe you can repeat
okay.
what you said about point 2.
Okay. So the point 2 says that the AI map intertwines these two involutions, and this observation actually was pointed out in Boch's paper. But there is not for this AMS map. This not for this choice of Ginzburg-Weinstein map, but for the one Boch created. And now, once we have a Poisson map and we have a Poisson differomorphism intertwine those Poisson map, one can get actually a Poisson differomorphism on their fixed locus. So here this circle just means because the fixed locus on we just pick one component such that the diagonal all equals to 1. Okay, that's good. Let's see how this involution look like for our example. So on this map, A goes to A minus A bar because here we use Hermitian matrices. It just means X goes to minus X and theta goes to minus theta. And so here you can say this matrix X goes to its conjugation inverse. So, and then it's, I write it as corollary because the proof is not that hard. And actually it's our new result. So if we take the fixed locus of K star under the map iota, one can check the minor of X equal the IK minor of X equals to this minor of X. And then one can take the limit, but now we restrict our Ginzburg-Weinstein map to SON. And this limit also exists. And all these functions will define a completely integral system on SON. So, yeah, so we want to actually, this works for SON. And if you know something about the Gelfand Zeitlin system for SON, this basically recovers the integral system there. And we want to generalize this result to SPN as well. So there's still some difficulties there. And for the parallel talk, I will explain more about how this.
Yanpeng?
Yanpeng, we can't hear you. unfortunately. Yeah, you might
He's
want
out.
to.
Yanpeng is out of the session. I tried to send
I see.
him a message, and
Okay, so he's probably reconnecting.
probably he's reconnecting.
Yeah. So we'll give him an extra 2 minutes, perhaps. It's unfortunate. One day we will all have super fast, like multi-giga internet, fantastic webcams, spectacular microphones. But then, of course, we were discussing this with Anastasia yesterday, that when that happens, of course, we will all be using like VR technology, 3D printers to print our food, and then we would still be complaining that the 3D printer isn't printing my sandwich quick enough.
Okay, Yanpeng is back.
Yeah. So, Yanpeng, are you able to? Yeah. Okay. Good.
Where I am?
Okay. Yes. Sorry. So.
You froze on the phrase about what you're going to say in the parallel session.
Mm-hmm.
Oh, okay. Yeah, in the parallel session, I will explain what the image looks like of all these functions and explain some relation of it with the Gelfand Zeitlin cone and some other interesting cones. Yeah, that's all I want to talk today. Thank you. Sorry for the internet.
No problem. No problem. Okay, thank you very much. Very interesting talk. Thank you, despite the technical difficulties. So let's all give Yanpeng a round of including emoji applause. Emoji applause. Everyone, click your emoji applause. Wonderful. Thank you. Okay. Thank you.